Sorry, I didn't hear you.
Not yet.
Not yet.
At least Christian gives the green light.
I said we will start at 9 in the channel. I think we can start like 9:01, and that will be okay. Oh,
Okay, but anyway, I wait for your explicit voice telling me that I can start.
I'll wait to have at least 20 people connected. I'll let you know.
Mm-hmm.
Okay, I think we can start now.
Okay, so hello everybody for the day 2 of the Homotopy type theory course. And I will start by reviewing shortly what we did yesterday, okay? So I first motivated the introduction of types historically, okay, with paradoxes. I briefly spoke about lambda calculus, and then also briefly spoke about Martin-Löf dependent type theory. So I tried to motivate the notion of dependent type from the point of view of programming, okay, with examples like lists. And then I started to introduce one by one the different type formers that we have in type theory, namely sigma types, pi types, identity type or propositional equality type, natural numbers, coproducts. What else did we have? I think this is more or less all. Booleans, okay, which are a special case of coproducts. Yes, and also two special types, 1 and 0, which are somehow the zero-ary versions of the product and the coproducts, okay? And okay, natural numbers, as I just said. And this is essentially what we did yesterday. And we discussed a lot the two notions of equality that we have at our disposal in type theory, namely, namely definitional equality on one hand and propositional equality on the other hand. And since there were some questions yesterday, I added a slide yesterday, so I might comment on it to try to convey even a bit more about the difference between these two kinds of equalities. So the question is that these two equalities, the way to prove them using the tools of type theory are quite different. So definitional equality is quite traditional, okay, in the sense that people are used to prove equations by by a sequence of equations. So if you want to prove, I don't know, that something A is equal to some A is equal to some B, well, maybe you will use a first equality and then a second one, etc., until you reach B. So usually this is how you prove definitional equalities, just by the tools of equational reasoning. While for propositional equality, it's the rules of the game are quite different. It's a type. Okay, it's not a judgment. It's a type here, and so we need to use the tools at our disposal to produce a term of this type. So it's a bit different. Of course, you can consider that a sequence of equalities from A to B is a proof that of A equals B, but here you might have other ways than just equational reasoning for proving a propositional equality. And usually you get such a proof by applying an adequate induction operator. We have seen that most of our types, actually all our types except the function type, come with an induction operator. So usually you will have an insight or be clever and find an adequate induction operator, apply this to an adequate type family of equality types, which will allow you to produce a term of these equality types. So you will use all this machinery of induction operators to find your proof. And for an illustration, I gave yesterday the proof of the subjective pairing. If you remember, it was that the proof that if we are in a sigma type, we can prove that PR1Z, PR2Z is equal to Z. Okay, so it's interesting because you can prove it. You don't need to assume it like you would do in normal textbooks on lambda calculus with products. You get this as an additional rule together with the rules that PR1 of x1, x2 is x1, and like this, PR2 of x1, x2 is x2. So usually in a textbook you would find these three axioms, and then if you are category theory oriented, you learn that these three axioms give the universal property for products. Okay, so here I can also make a comment with respect to questions that were raised yesterday on Discord. Maybe I go here. Maybe I go here. Yes, yes. So the comment is the following. So let me first discuss the slide, and then I'll make the comment. So except for the function type or the pi type, all the other types considered so far, and we will see more of them tomorrow or the day after tomorrow, which are called higher inductive types. We will see them shortly. They also share the same general pattern. So what is the general pattern? I have already stressed it, but let me repeat it. Also as a warming up for today. So you provide a new type former by first telling, giving a name to this, well, to say how you form this type. Okay, this is the first item here. Then you give constructors for this type. Okay, so here I have summarized those for the pi type, okay, because it also has constructors. The pairing for the sigma type, the in left and in right for the co-products, 0 and 1 for Booleans, and reflexivity for natural numbers. And I could have added here 0 and sucks for natural numbers. Okay, that's one thing. And then you have you have a principle, okay, for except for pi calculus, where you have a way to eliminate. So yes, you can consider constructors as introducing elements of your type, and then you want rules to eliminate. What does it mean to eliminate? Well, you have something of your type, for example, pi type. An application is an elimination because you take a function and you destroy it somehow by applying it to some element, and then you get a result of well, let me write it. You see that it's an elimination in the sense that if f is of type A arrow B, if I apply it to A, which is of type A, this is of type B. And you see that you have used your function, and that f in your use, the arrow type has been consumed in some sense. Okay, you produce something of type B. And the induction operators are also in the same spirit. It says, well, how can we use elements of some type? And the idea, for example, for natural numbers is that we, in the end, we show how to find, how to define function from of this type. Okay, for some family of type, depending on, yes, sorry. Well, okay, it could be an n, why not? Okay, it could be an n, why not? So it's pi n of type n, Cn. So you see that I explain in an induction operator, I give you some tools in order to define functions that take as input a natural number. So it's really in the same spirit as application. It's how a type is used. Okay, and then you have associated with your introduction rules and induction operators, you have equalities. And so far we have seen only definitional equalities in the definition of type formers. Tomorrow or the day after tomorrow, we will see an example, which is the example of the circle. Okay, this is a higher inductive type that we will see, in which there will be a recursion principle, an induction principle, and there will be one definitional equality associated with it and one propositional equality. Okay, and And then sometimes a uniqueness principle holds, okay, like the eta rule of the lambda calculus. I don't know if I mentioned it last time, but this is the eta rule. The eta rule here, okay. So remember, the beta rule is the main rule. Beta rule is this one, okay. So, and eta rule is a rule that you may want to have for certain applications, and but it's debatable whether this rule should be definitional or equational. And anyway, what is the meaning of this rule? It says essentially that in the pure lambda calculus, every term is a function. Okay, which is so a you see is an arbitrary term, and this axiom tells you that you can explicitly write it as the function lambda x, a applied to x. Okay, similarly, surjective pairing that we just wrote a few minutes ago says explicitly that every element is a pair of its two projections. Okay, so something that I want to stress here is that this is also quite similar to, well, at a certain distance, but it's quite similar to the approach that we have in category theory to define some structure on categories, like having products or like having function types. And these are called, in category theory, these are called universal constructions, in the sense that you give you give this by means of some universal property. Okay, I will not comment too much on this word universal property here, because I don't want to do a lot of category theory, but some of you already know about this because some people mentioned that in the discussions. So here I want to stress a little. So the idea is that the package formed by all of these, okay, introduction plus induction, amounts to give a universal construction. Okay, I will not go into the detail, but there's an interesting slight difference. Remember what we did for the sigma types. For the sigma type, we gave the constructor, the pairing, okay, and then we gave an induction principle, and then I showed you that from the induction principle, you can derive the notion of projection, PR1 and PR2. So in the type theoretic presentations, projections do not appear at first. Okay, they are not the important actors. While in the categorical definition of the same notion, well, let's say the product, not the dependent one, the usual product. If you have some knowledge of category theory, you will probably remember that a product is given first by projections. You say that you have, for any given objects, okay, this is how you call types in category theory, you call them objects. For any object A, you have an object that you call A times B together with projections from A times B to A and from A times B to B, such that some universal property holds, which I'm not going to do here. So you see that projections come first, well, and the universal construction tells you that there's something called the pairing. Okay, the universal construction says, well, let me do it. So what is the universal construction? It says that if you have any object C, if you have two morphisms from C to A, sorry, because I have to use the categorical vocabulary, but let's think that these are just types. And suppose that I have a function from C to A and a function from C to B, then the universal property says that this from all these data, you can derive a function from C to A times B, okay, satisfying a universal property. But this function is essentially the pairing, okay? You pair the two functions. So you see that the pairing comes after the projections, while here the pairing comes first and the induction principle comes next, and the projections are derived from the induction principle. So I don't know what to make of this remark, but it's just to tell you that the type theoretical language is speaking about the same things, but from a slightly different perspective. Okay, so now that I have made these general remarks, I think we can start the lecture proper, okay, and arrive to where we were exactly. So we were exactly discussing the induction principle for the identity type. So this is so important that I'm going to repeat it, okay? Because I know that this induction principle is so magical that sometimes you need to think hard of why this is simple, and you can also make mistakes because it is very simple and it's very easy to misuse. Okay, so the important word in this slide is the word generic here. Okay, so let me repeat now in English, using English. Okay, so maybe I comment this slide here. So I will, this is the official induction principle with its type, okay, and with its associated definitional equality. Now, in English, what this induction principle tells me is the following. If you are given a family of types C that depends, okay, this is this family here, that depends on X of type A, Y of type A, and P of type X equals Y. And okay, and this is a type. So suppose that you have a type family of this parameterized by X, Y, and P. Then, if you want to define a function, a dependent function, that will take an X, a Y, and a P and return an element of C, X, Y, P, all you need to do is to define this function that you want to have. You just need to define it for the triples formed by an X, the same X, and as P, you take the reflexivity of X. Okay, and something very important here is that this principle works only if everything here is variable. So this X and Y have to be able to range over all of your type A. Otherwise, it will not work. Okay, so now, why should this hold? Well, the idea, maybe I try to draw this here. The idea is that it comes really from homotopy. The idea is that suppose that you have a path. Okay, let me try to use this. Okay, suppose you have a path like this, from some point to another point, from some point here to some other point. What you can do with this path, you can deform it. So you can, for example, shrink it, okay, along itself, okay, and shrink it in this way, shrink it in this way, shrink it in this way, until you get just a point. And a point is just, when the path is reduced to a point, it's the reflexivity, okay? So the idea is that you can deform any path to the path which is a pure reflexivity, provided you have the ability to move both ends of your segment. Okay. Now, actually, another principle, another induction principle holds. Yes, it's written here. Okay, so let me read for you this other induction principle, and we can show, that will be the next step, we can show that this other induction principle for identity types is intercodable with the other one. So it's another principle that has exactly the same power. So let me read it. In this other version of path induction, which is called the based path induction, you fix one end of your path. Okay, so let me read it. What this says is, suppose you want, so you suppose that you have fixed X. Yes. Yes, maybe here I should have put parentheses, that would have been more clearer, I think, if I put parentheses like this. Okay, so suppose we have fixed one end of your path. Okay, so let me call it X. So you have an X that is fixed, but Y remains variable. The other end of your path remains variable. So the question is, how can you build, given that X is fixed, how can you build a function that will take any other point, Y, and then any equality that X is equal to Y, so this X is fixed, but this Y is varying, and produce an element of DYP? And the answer given by this induction principle is that you can produce such a function, provided you define it in the special case where Y is your X and where P is the reflexivity. So it's the same idea. Everything is reduced to reflexivity, but here you have first fixed one point. Okay, so now what is a geometric image? Well, the homotopy explanation. It's exactly the same as before, but the explanation is, well, it's the same but slightly different. So I'm not allowed to shrink from both ends. I'm only allowed to shrink from one end. But you can see I can do this perfectly well. Okay, I don't need to move this extremity. I can progressively deform my path until I get to the reflexivity, and this justifies. This is a homotopical, the topological justification for this principle. Okay, so this is another induction principle, and okay, let me do it in English, but I think I did it, but let me repeat it. Suppose that we have fixed some A, okay, in A, and suppose that we have a family of types DYP, that this family now depends only on Y and P rather than on X, Y, and P, because the X has been fixed to be A, okay? In order to define a dependent function in this type here, which I already commented, all we need to have is its value at A ref of A. Okay. Now you may ask, if you fix X and Y, can we do anything? The answer, of course, is not. Is nothing. Because again, let me do the picture again. If both my ends here are fixed, no, it must be fixed, sorry. If both my ends are fixed, I cannot play this game. I could, well, I can probably try to deform this path, maybe I will reach this path or this path. But since I don't have the possibility to move one end to the other end, I will certainly never get to the reflexivity. So that's why we need at least one of the endpoints of my path to be variable. This is why if we take the 2 points to be variable, we have the standard and official induction principle called path induction. And if we fix one and let the other vary, we have this thing called based path induction. Okay, great. So now what I can do is to give you, so this is the first really technical slide in the series of lectures. It happens that the proof that these two induction principles are codable from each other is highly non-trivial. Okay, and well, there's one direction that is easy, the other direction is not so easy, and it is due to Christine Paulin, okay, whom I'm happy to mention here because she's the only woman winner of the famous award that was awarded to the Koch system by the ACM, okay, the most prestigious software award. And well, there were a number of winners for this prize, mainly the the most important historical contributors to the Koch system, including Christine Paulin. Okay, so let me try to explain her proof. So first of all, suppose that we take int prime. We want to show that int is derivable. So here is the definition. Okay, so if we want to show the induction principle applied to some family C, okay, so here maybe I should type things in order to understand them. So C should be a family depending, so maybe I write just C, X, Y, P, just to remind you that this family depends on X, Y, P, okay? And then this C, what is the type of this small c? So we should go back here. The small c here should return an argument in C, X reflex, okay? So let me write it. Okay, so we have to remember that a C like this, okay, is such that Cx is of type Cx reflex. Okay, and now we need to repackage all this information. Okay, and then X and Y are elements of A, and P is a proof that X is equal to Y. We need to repackage all this information to make it digestible for int prime. Okay, so in prime we will first need to fix some element of A. So we pick X. Okay, so that's the first argument here. We put an X here. Maybe I put them here. So I apply here to some X. And then I need to find a family that depends only on Y and P. Well, the family Cx is a very good candidate, okay? Because C applied to X has fixed X, and this is precisely of the type Py, okay? C was of this type here. But after application to X, it's only of type, the X here has disappeared. So it's of type pi Y of type A, X equals Y. So this is correctly typed. Okay, so this is okay. And then my small c should be of type dx ref x. Okay, so let me be very slow. Okay, this Cx should be of type dx reflex. Okay, but we defined d to be Cx. Okay, so this d is actually Cx. So I can replace this d by Cx. And this is exactly what little c here is. The c was here. This was my little c. Okay, so c applied to x is of this type. And finally, y and p, and these do not need any special comments. So you see that you can this type checks, okay, and as often in programming, when you know that something type checks, you already have half of your well, more than half of the way done. Of course, you need to show that the definitional equality that you expect for int is derived from the one for int prime, but I will omit it. Okay, so the ID for the converse is clever. What we need is to use some trick which has to do with polymorphism. So I already mentioned polymorphism yesterday. So I don't want to try to synthesize this definition. So let me just explain what is written in the slide, which is a bit magical. So we need, the idea is that now we have int that is given, and we try to find int prime. Okay, so we need for any type D, for any type family D, like this one, okay, we need to find a clever type family C to which we shall apply induction in a clever way. So here is this C. Okay, so let me read it. So C is, yes, C does not mention D. That's important. C does not mention D. So this is why it is polymorphic. Okay, so it's a type family by itself. Okay, that is not directly related to D, but of course it is done in a way that everything will work. So let's see. So it's a type family. So it takes a x, a y, and a p, and returns a type. Okay, and this type is polymorphic in the sense that it takes a type family. Okay, which is this an E. Okay, and this E has the same type as our D, by the way. Okay, the D that we have in int prime has this type. Okay, and here we have exactly the same type. Okay, but instead of taking D, I take a variable D. Okay, this is why I call it E. Okay, so my C is this type, which is the type of functions that take a type family like this. Okay, that take a type a type family like this, yes, and return this function type, which is, well, ex reflex to eyp. Okay, so you see, of course, that here we try to anticipate what we want, because in the end we want something like that. We want that from an elements of dx reflex, we want to have a general element of dyp. Okay, but again, this E is variable. Okay, so this is a perfectly decent type family. Now, I apply this type family, apply the induction principle for the official one, the int principle, to this family C. Okay, and then I need to find an appropriate function. Okay, so here is this function. So what we expect here is a function. Did I write the type? No, but we know the type. We know the type. This function here should be of this type. Here. So it takes an x, okay, and it should return something of type Cx reflex, okay. Yes, okay. But what is Cx reflex? Did I write it? Yes, I wrote it. So we expect this function here to be of type Cx reflex. Sorry, we expect this body here to be of type Cx reflex. Okay, so let me try to overload this. We want to no, maybe I use this here. Maybe I use this here. So we are now working on this expression here, and we want to show that it is of type Cx reflex. Okay, but what is Cx reflex? So if I instantiate C by applying it to X reflex, what I get is PE EX reflex arrow EX reflex, because Y is instantiated to X and P to reflex. Okay, so I look for a function of this type. And okay, so this function, there's an easy one. You take an E, okay, and then you take the identity, because this type is the same. This type and this type are the same, so you can take the identity function, namely lambda EE. Okay, so this type checks correctly. And then, okay, then when you have done this, you are here in this expression. So you remember you have your induction principle, you have applied it to some C, okay, so you've done this, and then to some miraculous function, which is this lambda x capital E lambda identity, which lives here, okay, and so the induction principle returns some function here, which you can continue to apply. Okay, so you apply it to A, and then to Y, and then to P. Okay, so once you've done this, you get something of type CAYP. But what is CAYP? Okay, CAYP, it's this expression here. Okay, with A instead of X. Okay, so it's this expression here is of type this thing here, where X has been replaced by A. Okay, so because it is of this type, I can continue to apply this expression, because it starts with a pi E. So I apply to D. Okay, so now I'm here. Okay, where now the E is D, my original D, and this is where the original D makes its appearance. Okay, so when I have applied to D, I am exactly here, where I have replaced E by D and X by A. So what I have is this type here, which I have here. D A roughly arrow D YP. Okay, it's obtained by substituting D for E and X and A for X in this expression. And finally, I can apply it to the small d, okay, because now I have to explain the left-hand side, because this is the left-hand side that I'm trying to define. So according to the prime induction, what I need to do is to apply it to some A and then to some capital D, and then to some yes, and then so to some element of dx reflex, okay, but because I applied it to A, this is of dA ref A, hence this small d is of type dA ref A. So here, this d is of the correct type, because if you remember correctly, when I have done all this sequence of applications, I find myself with a term of this type. So if I can apply it to D, which is of the correct type, and what I get is an element of DYP. And this is exactly what we want, because int prime in the end, after making all these applications, should return something of type DYP. Okay, so again, this definition type checks, and hence it works. Okay, and it is clever. I mean, this is the kind of exercise, if you just give it to an exam, well, there are high chances that you don't receive an answer. It's the solution is elementary, but it's clever. Okay, good. So this is the first technical proof ever in well, serious technical proof in this series of lectures. There will be a few more. Okay. Now, well, let me summarize, because I have a summary here. So here are all the induction principles that we have so far. The one for sigma types, so co-products, Booleans, natural numbers, and identity types. And okay, and yesterday I finished the course by starting to use path induction to understand well, the structure of identity types. There are many things to do with identity types, and we started yesterday by showing how to concatenate paths and how to give inverses to them. And I even showed you yesterday that you can prove the laws of a group for the equality of paths. Okay, so here I should mention that if I speak about dimensions in terms of topology or geometry, we have two dimension zero. Well, yeah, we have dimension 0, dimension 1, and dimension 2 that come in. Okay, so dimension 0 are the elements of my type A. So maybe I should repeat the picture of yesterday here. So yesterday I gave you this topological view where my type is A, and points, well, inhabitants of A are points. That means they have a dimension 0. And then I told you that paths, which are proofs of the equality of elements, well, sorry, I told you that a proof that X is equal Y, okay, this is X, this is Y, this is P, they are paths, and a path is typically a curve, and it's of dimension 1. And now, these equalities here, and others, all these others, they live at dimension 2, because this is this is a propositional equality. So in order to prove that they hold, what you need is to exhibit a homotopy between, these are two paths, okay? And what you need to find is a homotopy between them, okay? So for example, we need to find a homotopy from P.Q.R to P.Q.R. And it's quite amusing to see that if you open a topology book, okay, you will see that, of course, it is an elementary proof that there is a homotopy between them, but the proof is usually not so easy, because, well, let me make this small digression. In topology, a path, okay, is defined as a function from the interval 0, 1 in the sense of the real numbers. So this is a real segment from 0 to 1 with all the elements in between, all the real elements in between, that goes to my space A. Okay, so this is called the interval, okay, and a path is defined as a continuous function from this interval to A, okay, and then what you do if you concatenate P dot Q, well, you have two functions from 0, 1 to A, and another one from 0, 1 to A, and then you do something that looks like obvious. You want to concatenate them so that you want to define a new function from 0, 1 to A that starts as P and continues as Q. So one way to do this is to reparameterize P so that now P is going from 0, 1/2 to A. And then you reparameterize Q so that it's going from 1/2 to 1A, and then you concatenate the two. Okay, and of course you need to make sure that that the endpoint of P is coincides with the starting point of Q. So you see that you need to reparameterize, and when you do P.Q.R, it means that you give 1/2 here, and you give 1/2 here. Okay, but again, this is, you give 1/2 for P.Q. So in the end, you give 1/4 to P and 1/4 to Q. When I mean 1/2 or 1/4, it means you think that there's a guy running from P of 0 to P of 1. So somehow you ask R to take half of the time he was taking before, and you're asking to P to take 1/4 of the time that he was, to run very, very fast, 1/4 of the time that he was running before, and Q. And you see here that the division of speed of acceleration that is required by these way of parenthesizing the three paths is not the same. Okay, so here you give 1/2 to P, 1/4 to Q, and 1/4 to R. So these paths are certainly not the same functions in terms of topology, but you can clearly show that they are homotopic because your time is continuous. So you can clearly smoothly go from this division of time to this other division of time. So this is to show you that in topology, really these things do not coincide. Hence, if they do not coincide, in topology, you cannot ask them in type theory to be definitionally equal, because definitionally equal things will be interpreted in the mathematical model as things that coincide. Okay, while here we really have in topology a homotopy. So this is another reason why propositional equality is more faithful to the topological intuitions. Here, it would really not make any sense in this homotopical interpretation to ask for definitional equality. Okay, so the next task is to define something that is called app. Okay, this thing here. So if you have a function from A to B, this function should also be able to map proofs of equalities to proofs of equalities. So in the language of category theory, it should be not only a function, but a functor. So it maps points to points, but it also maps paths to paths. So what we seek is, given x, y of type A, so f is fixed, given x and y of type A, given a path P of type x equals y, we want to define a path from fx to fy in B. And this guy, we don't need to postulate it because path induction will give it for free. Okay, so this is another very simple instance of use of path induction. We want to find this app, but because x, y, and p are all varying, we only need to define this app in the case app f x x reflex. And for this, we have a very simple solution because we need to find an equality between f of x and f of x, and we just take the reflexivity of f of x. So you see that we can define app in just one line. This is the magic of path induction. So now there's a question. If instead my f here was a dependent function, so if my f here was of this type here, pi x of type capital A, bx, then something happens. So maybe I should make a drawing here. Something happens. So suppose that I have my f of type, maybe I use a better red. It will be easier to read. Yes, I think this red will be more visible. So I have my f from of this type. Okay, so somebody in the audience yesterday said that this was the type of sections, and he was right, and this picture will show it. So we can imagine this type family. We can picture it like this. Okay, here we have our type A. Okay, and here we have typical examples of elements of A, and here we have a typical path from X to Y, and all of this is in A. Now, B is a family of types, which I can represent by saying that above X, I have the type Bx, and above Y, I have the type By. Okay, and then what? And then f is a function. So f of x is in Bx. So here is my f of x. F of y is in By. So here is my f of y. And you see here that it doesn't make any sense to write such a thing that f of x is equal to f of y, even if x was equal to y, because there is a path P of this type. This doesn't make sense, okay? But there is another very important operation that we are going to be able to define using path induction, which is that there is a mirror of Fx living here. There is a guy living here, and this guy will be called transport B P X. Okay, so this is my next task. My next task is to define this guy, and then I will return. Well, no. Let's anticipate that we have done this step. Then we can postulate the existence of, from the existence of the path from X to Y. Okay, we can postulate the existence of a path that relates this transported Fx, sorry, it's transport P Sx here. Transport Fx. Okay, and what we shall prove is that we have an equality between transport B P Fx and Fy. This is what we shall prove. So we have two tasks. The first one is to define transport, and the second one is to find an element in this type, which we shall call, so this guy, we will call it app D. Okay, this is like the app of the non-dependent case, but I add a D to stress dependency. So this guy will be defined, will be by we will define one guy witnessing this equality, and this guy will be called AppD applied to F and P. Okay, so it's the morally it is the dependent version of app applied to F applied to P. Okay, so with these topological explanations, we can start and define first transport and then AppD. Okay, let me check with time. Yes, I can. I spoke for about 1 hour. I will take 20 more minutes and we will make a break. Okay, so how do we define transport? Well, by applying induction, of course, but we need to find the appropriate scenery or setting for this. So we need a family, we need a type family. And this type family DXYP will be the arrow type, the function type CX arrow CY. So it depends on X and Y, but does not depend on P. So it's fine, it's fine. You may have dependent families that do not depend on all their parameters. That's fine. Okay, so we have a D, okay. And now in order to apply the induction principle, we need to find a function that goes into D, that takes an X and goes to DX reflex. Okay, so because Y is repeated and it's just X, we need to find a function from CX to CX. Okay, but there is one, the identity. Okay, so this is correctly typed. And if I apply the induction to D and to this function here that takes X to the identity on CX, then the induction principle tells me that I have a general function that takes X, Y, P and returns a function from Cx to Cy. And this is the function that I call transport. So this transport will do the job because, okay, it takes an X, a Y, and a P. So we will abbreviate this as, instead of writing, because it would be too heavy, instead of writing transport C yes, instead of writing transport C transport C X Y P, okay, I will omit the X and Y, just not to be too heavy. So transport P is a function from Cx to Cy. So if I apply it to an element, let's call it U, okay. If I apply it to an element U, which is of type Cx, then this thing here is of type Cy. This is exactly what this type says. So this is exactly what we wanted. Remember that the picture was this one here. We wanted to go from bx to by. Okay, okay. Now this b is a c, but up to this renaming of b in c, I think it's okay. So you see that I have defined transport. That's the first task. And maybe I didn't write it explicitly. I didn't write it explicitly, but what I know is that coming with the induction principle, I know that transport C applied to ref and to U is, because here I have the identity function. Okay, so it should be the identity function applied to U, so it is U. So transport will always satisfy this axiom, and I will make sure to make it appear in the final version of the slides, because apparently I omitted it. Because I will use this definitional equality later. Okay, so so we have associated with transport, we have this additional this definitional equality, which tells me, okay, if there's nothing to transport, please do not introduce noise. That's the idea. If this path is nothing, it's just the reflexivity, then there should no transport should happen. So transport P U should just be U in the case where P is ref. Okay, so that's again for transport. Now we need to define ABD, okay, which, as I just told, should be transport applied to P and then to Fx, okay, equal Fy. So morally we want Fx to be equal to Fy, but we need to transport Fx first in the same fiber, or in the same in the same member of the family, by. We need to transport it before we can state the equality. So how do we prove this? Well, okay, so again by induction, because you see that this ABD depends parametrically on X, Y, and P. So again, because this is generic, we can restrict ourselves to X, and ref, okay? So in this case, what we want to define is an equality between transport ref Fx, but we've just seen that this is definitionally equal to Fx. So in the case where P is reflex, this guy reduces to Fx, okay, equals Fx. And there is such a term, namely the reflexivity. So we can define ABD to be to be ref Fx in this case, and then by path induction, I have defined ABD for in every case. Okay. So we will see many properties of transport. Okay, but let me try to do some conceptual slides before we go to some technique about transport and applications, etc. So here I'm going to define, try to define different notions of equivalence that we will use later on. So there is a first notion of equivalence, which is called homotopy. Okay, because this is exactly the counterpart of two maps being homotopic in homotopy theory. So the first definition I give in this slide is this one, and I have a symbol for it. Okay, so I use this symbol, which is in LaTeX sim. Okay, and I will say homotopic. Okay, so I define F to be homotopic to G in the case that this type is inhabited. Pi x fx equals gx. Okay, so why does this have to do with homotopy? Okay, that's interesting. Yes, I don't know exactly how to picture it, but let me try. This will be suggestive, not really formal. So you have to imagine that F is something like that, and that G is something like that. Okay, and that this is f of x, so it's a curve. Okay, let's see that f is a curve, and at x, okay, and here you have the x axis. Okay, and here you have the y axis, and so this is f of x, and this is g of x. Okay, and then well, if and this is x here on the axis. Okay, and you see that if I have an equality between fx and gx, it means that I have a path. Okay, so if I can do this for all paths, you see that I can fill the space between f and g. Hence, f and g can be deformed one to the other, and they are homotopic. Okay, so this is a suggestion of the topological meaning behind this type theoretical type. Okay, good. So this is called also pointwise equality. If we stay on Earth and do not go into topological pictures, it says that pointwise. So for each x, I have a proof that fx is equal to gx. Okay, an inhabitant of this type is called the homotopy from f to g. Okay, and this is one definition, which is now used in a more important definition, maybe a fundamental definition for this course, namely the definition of when two types are equivalent. So two types A and B are equivalent if I can provide a function f from A to B, a function g from B to A, and a proof that the composition f composed with g is homotopic to the identity, and a proof that g composed with f is homotopic to the identity. Okay, so if, as we shall do in a moment, if we consider this notion of equivalence between functions as being the right thing to say that f and g are equal, okay, and we will see that this is an axiom in type theory, which is called function extensionality. So we will see this axiom in a moment. But well, imagine that we already have this axiom. So you can read this as saying that f and g are equal in the sense of identity type. So they are there's a proof that f is equal to g. So here, what this says essentially is that in up to propositional equality, F has an inverse, which is both a left inverse and a right inverse. Okay, so, okay, in usual set theory, if you have two sets, when do you say that these sets are equivalent? Well, when there's a bijection between them. Okay, when you have two maps, F and G, that the first is the composition here is the identity, the other is the identity. Here, it's the same idea, except that it is up to homotopy or up to equality, propositional equality, once we will have the function extensionality. Okay, so this is the notion of A and B equivalent, being equivalent, and it is quite useful to first mention the existence of F, okay, and then to package the rest of the information. So we fix F first, and we package the rest of the information that we have a G and a homotopy from F composed with G to the identity and a homotopy from G composed with F to the identity. We package it into a new type, which we call Q-inv of F. And Q-inv means quasi-inverse. Okay, so this stands for quasi-inverse. I will also write this explicitly in the final version, quasi-inverse. Okay, and I will use this notation when this happens. So if I can produce an F, that's that Q-inv of F, then I will write that A are equivalent with this notation. And this notation is not in the books, it's just my notation, but I found it quite useful to have it. Okay, good. This is one notion of equivalence between types. And this is really a good notion, okay? But you also have a weaker notion. This weaker notion that relates to types is called the logical equivalence. And in this weaker notion, which is really inspired by logic, we just require that A implies B and that B implies A. So what does it mean from type theoretic point of view? Is it means that you have a function from, you are able to exhibit a function from A to B and a function from B to A. And you don't require the rest. You don't require this, you don't require this. And then you call this logical equivalence. And I have this notation, which is also a personal notation, I believe, for logical equivalence. Okay, good. Maybe, where are we? Yes. Yes, okay. Before the break, I want to skip, because these slides are a bit technical. I prefer to do them after you refreshed your neurons for 10 minutes. So let me finish by something that is related to what I just said. So here is an example of logical equivalence. So I should probably repeat here what is the definition of Q-inv. Okay, so I repeat it. So Q-inv of F was, by definition, the existence of a G of type B arrow A, such that F composed with G is homotopic to the identity, and G composed with F is homotopic to the identity. I hope I wrote it exactly. Yes, this is not particularly readable. Let me check. Let me check that I repeat exactly. Yes, okay, good. So we are going to prove that these two types are logically equivalent. So let me comment on the other type. So it's a bit different. It says that F has a right inverse G and also has a left inverse H. So if you've done some elementary courses in groups, okay, in an algebra course, you will probably remember that if an element has both a left and a right inverse, then these two half inverses actually coincide. Okay, that's something that's a typical argument, and we actually it's reproduced below. So what we are going to prove, so morally speaking, these two types should be the same. But okay, actually it is completely false. What I just said is completely false. These two types are by no way equivalent in the sense of this equivalence here. And we will see later. Okay, we'll see later. And it's, well, I will not prove it because the proof is tricky, but we will see later that this yes, not exactly this. Do I see something wrong here? I don't. I might see something wrong, but anyway, I will correct it later. And this happens to be a proposition where this happens not to be a proposition, but I didn't tell you what a proposition is, so it comes next. Some types are propositions, some types are sets, some types are groupoids, and etc., etc. So there are reasons not to identify these guys. But on the other hand, they are logically equivalent, and this is what I'm proving here just before the break. So we cannot expect more than this, but this holds. Okay, so we need to find a function from Q_inv of f to a bi_inv of f. So this is the easy direction, because if I have a quasi-inverse, okay, I can use it as a witness that it is a right inverse, and I can use the same G as a witness that it is also a left inverse. So the direction from Q_inv to bi_inv is easy. Okay, we can define a function that goes from here to here. It maps a pair. Okay, it maps a pair T followed by epsilon followed by eta. Okay, so epsilon is an element of this type. Eta is an element of this type. It brings this element to so it's a product type. So you take G paired with epsilon, and you take G paired with eta. Okay, and this is correctly typed. So you need to find a pair of two things. The first thing is of this type, the second thing is of this type, and you see that G epsilon is of this type and G eta is of this type. So this is the easy thing. In the other direction, suppose that we have a G and a H. We need to find a G that is both a left and right inverse. So clearly, if I have a G and an H, okay, so what we can do is to take this G, okay. We already know that it is a right inverse by this, and we don't know yet that it is a left inverse, so we have to prove it. But the first thing to prove is that we are going to prove that the G and H that are here witnessing that we have bi_inv of f, so that comes with the data of an element of bi-inv of F, we are going to prove that they are homotopic. Okay, so, and this is the argument that you find in textbooks, in group theory textbooks. So if you start from G, okay, by the axiom for G, we can put, by the axiom for H, we can put H composed with F in front of G, okay, because H composed with F is homotopic to the identity. Okay, so this supposes that we have proved before something which is this property. Yes, we have to prove that homotopy is a congruence. So we have to prove something like this, and we will prove it, okay, after the break. We have to prove that if F1 is homotopic to F2, then this implies logically, okay, that F1 composed with G is homotopic to F2 composed with G. So we will prove that after the break. So assuming this, and of course we will also have to prove that G composed, that id composed with G is homotopic to G. Okay, so suppose that we have all this, then we can say that G is homotopic to id composed with G, but id is homotopic to H composed with F. Hence, by congruence, which is here, I have that G is homotopic to this, and then because these are actually equal, this is definitional equality, yeah, because composition of functions is clearly definitionally no, sorry, it's homotopic. It's also homotopy, but we also have to prove it, but we prove it for each argument. So what we have is, yes, I should stop, but what we have is argument by argument. By definition of composition, we have that these two guys are H of F of X. Okay, this is H composed with F applied to, sorry, H of F of G of X. And here the same. So these actually you have a definitional equality between these two things because they are the same. Okay. Okay, so it's an interesting instance of how to show that the two maps are homotopic. If pointwise they are definitionally equal, then they are homotopic. Okay, because definitional, as you remember, implies propositional. And remember that the definition of homotopic refers to equality, not to propositional equality, not definitional equality. Okay, so let me hurry and finish this proof, but everything is in there. So I'm there. I started from G. I write here. I applied associativity, and then again I apply the other information that F of composed with G is the identity. Hence, I have a proof that G is homotopic to H. Okay, but from the information that I had H composed with F homotopic to the identity, from the information that G is homotopic to the identity, again by congruence, I have this, okay? By transitivity of homotopies, another property to be proved, finally, I get a proof that G composed with F is homotopic to the identity. Hence, from the data proving that I'm in bi-inv of F, I can provide the data proving that I'm in Q-inv of F by combining all these homotopies. Okay, so that's all. And we make a break and start in 10 minutes from now. Okay, so in the meantime, I will read the questions. Okay.